So back again at the Origins 2026 conference in Paris, an astrobiology conference, very international and very interdisciplinary. I'm with a very renowned astrobiologist, the director of the Carl Sagan Institute at Cornell University, Lisa Kaltenegger. How do you pronounce your last name,
Yeah,
Lisa?
perfect. Kaltenegger, all good.
Kaltenegger. Okay, so we were just discussing some of the challenges in astrobiology, and I applaud you because it's been very hot the past 2 or 3 days. But you're a keynote speaker tomorrow. You're an invited speaker, and you have been almost at every session asking pertinent questions after every talk. And I just, wanted to know, what have you taken away thus far from this conference? We were just discussing in the interview about, you were saying that astrobiology needs to be more interdisciplinary. So tell us what you've taken away from this conference and what we need to do.
So, one key thing is that to find life in the cosmos, we need everyone. No, astronomers alone won't be able to do it, biologists alone won't be able to do it, chemists alone won't be able to do it. And so, a conference like this is amazing because you get people together who might not have thought about astronomy for the biology side, or astronomers who haven't thought about the biology side, or the chemists. Put everybody in a mix and get the discussion going. This is also why I enjoy actually asking these questions, because it's a different angle that I see research under than the person from a different field who's trained differently sees it under. And this, I think, is where the breakthroughs happen.
And so right now, there are 6,000 known or confirmed exoplanets, according to the NASA archive, correct?
So there are more than 6,000
More than 6,000.
planets that actually circle other stars, not our sun.
Right. Exoplanets, extrasolar planets.
And I think that is amazing because each of these planets is a puzzle piece of how planets are born, how they evolve, and how they function. Especially for rocky worlds like ours, we have a big gap in our understanding because we can see the Earth right now, but the further we go back in time, the harder it gets to tease out what the most important effects were that changed our planet. And then, of course, going forward into the future, that's even more difficult because we only have models to do that. My wildest dreams, we actually gotta have enough time to look at least at the rocky worlds within the habitable zone that we know of. And currently that number stands at 45, but it will go up and up and up with every year with all these discoveries. However, we have learned, for example, with the James Webb Space Telescope and looking at TRAPPIST-1, that we need more time to tease out the signal of these small planets.
Mm-hmm.
So realistically, I would say probably to a good degree, so we can actually say whether they have signatures that indicate life, 5 to 10. But to a coarser degree, I would say about 50. And that's exciting because those 50 will let us go into details in the right 5 to 10 that give us the highest chance to find signs of life if they're out there.
So what are the takeaways, a couple of takeaways that you picked up at this conference? What seems to be the trends in astrobiology in general?
I think especially at this conference, some of the takeaways that I've taken, especially at this conference, some of the really interesting things for me were that there's much more lab experiments going on right now. That is critical because a lot of the information we just don't have. So for example, how does biology respond to huge radiation? What are the things that actually can develop under different kinds of light from different stars? And that combination of people in the lab coming to conferences like this and telling what's possible to observe, modelers using them, and observers going after the features, that is a key component for us to be able to find signs of life out there.
And so the last thing I want to mention is that I didn't mention in the interview, is our Venus Earth system, which is, we don't really know how unique it is. We do know they're extrasolar Venus. Tell us what you consider an extrasolar Venus.
So what's really exciting is that among these 6,000 planets around other stars, we have dozens and dozens. We actually have hundreds in what we call the Venus zone that can be hotter than Venus, but it goes to the point where we think, if you go further away from the star, that you start to lose the water.
Right.
So basically, starting losing the water to all the way super hot is how we define the Venus zone.
Mm-hmm.
But we just submitted a paper that's not out yet that actually shows what are the 17 planets, or we just submitted a paper that shows what are the dozens of planets that are sitting in this transition zone between the energy that an early Earth got and the energy an early Venus got. Because somewhere in there, you lose your water and you lose your habitability, and we do not know where that is. So while I'm excited about exovenuses, I'm even more excited about these rocky worlds that just get a little bit less energy than Venus and a little bit more than a young Earth, because they will teach us about the limits of habitability.
So there's synergy between the work being done on exovenuses and our understanding our own Venus.
There's a huge synergy going on between the work that's been done on Venus, on Earth, and on exovenuses and exo-Earths in these planets in the transition between them.
And so studying extrasolar planets is not just a thought experiment. I mean, we are understanding our own planet by studying exoplanets, correct?
One key point in the search is not just to find life, even though I want to find life in the cosmos, but a second really important point is to understand our own planet and how it works and how to actually safeguard it better. Because with every other rocky planet we find out there, we understand a little bit better how rocky planets work. And that, whether you're interested in the search for life in the cosmos or not, should be important for you, because it's our planet and our future.
So what do you say to people in this age of uncertain funding who say, we have enough problems here on Earth, we don't need to be worried about some planet circling a star 1,000 light years away? How do you respond to that?
When you look at our exploration of other planets, it's easy to say, well, where is my real benefit? But what we're learning about these other planets actually teaches us about how the Earth functions in a much more detailed way.
Uh-huh.
And so what we need to figure out, this is how I explain it to my students, is, for example, if we find, let's say, 50 other Earths older than ours, and this is just a hypothesis, we haven't found them yet and we cannot do the atmospheres yet, but let's assume all of them show a lot of SO2 in the atmosphere. We know they're Earth-like, we know they're older than the Earth. That doesn't mean that this will happen to our own planet, but it does mean that it would be intelligent to develop a technology that can filter out SO2 off our atmosphere, because we can breathe it. So it gives us a glimpse into our possible future, and I think it's important to be prepared if that future might not be the best geological opportunity for humankind.
And that's sulfur dioxide, is that,
Sulfur dioxide, it was just an example, but it comes out of volcanoes.
Uh-huh.
And so if every older Earth would show that, then that would be puzzling. But in that puzzle, because it's every other older Earth, we would probably find the motivation to figure out to get rid of this gas or other gases that we could find, just to make sure that this doesn't happen to the Earth, or if it does, that we're prepared.
So thanks so much, Lisa, for your time today. You've been very generous, and we look forward to hearing more from your research. Thank you for speaking to us.
Thanks for having me.